2025 A-Level Combined Mathematics Paper 2 Part B question number 16. This question has to do with center of mass. The question says, show that the center of mass of a uniform hemispherical shell of radius A is at a distance of A over 2 from its center, and the center of mass of a solid uniform right circular cone of height h is at a distance of h over 4 from the center of its base. It then says, a frustum of height 2a is made from a solid uniform right circular cone of base radius 3a and height 3a by cutting it through a plane parallel to its base and removing the smaller right circular cone. So we can see here, we initially had a cone of height 3a and base radius 3a, and we cut the tip of it such that we are left with a height of 2a here, meaning that the cone that we cut here had a height of a and a base radius of a. So when you remove it, we are left with this object right here, which is what we call a frustum. So it says the mass of the right circular cone removed to form the frustum is m. Given this, it says show that the mass of the frustum is 26m. So basically the mass of the entire cone here was 27m, and when we remove the top part which has a mass of m, we're left with 26m. So we need to show that it's 26m. It then says a uniform hemispherical shell of radius a and mass m and the above frustum are rigidly fixed to the ends of a uniform rod of length lambda a and mass m to form a composite object such that the rod, the center of the hemispherical shell, and the axis of the frustum are all lying on the same straight line as shown in the adjoining figure. So we can see here this point right here, which is the center of the hemispherical shell, the rod, and the center of the frustum are all in the same line. So given that it says show that the center of mass of the adjoining composite object is at a distance of 3 over 56 times 15 plus lambda times a from the center of the large circular base of the frustum. So from this point, if we go up, the center of mass of the entire system here is going to be a distance of 3 over 56 times 15 plus lambda times a above this base's center. So given that it finally says the composite object is placed on a horizontal table with the curved surface of the frustum touching the table. It then says the adjoining figure shows the vertical cross section through the axis of symmetry of the composite object and asks us if the composite object is in equilibrium, show that lambda must be some value less than 11 over 3. So basically for this particular situation, we can find some equations here and we can show if we have this point and the center of gravity here or center of mass here is beyond this point, then the object is going to topple. So if it doesn't topple, it must mean that the center of gravity here or center of mass here is somewhere in this region, meaning it's after this point, which is going to be the critical point, and using that condition, we should be able to show that lambda is less than or equal to 11 over 3. So let's start with this question. So for the first part of the question, they are asking us to basically find the center of mass of a uniform hemispherical shell and also the center of mass of a solid uniform right circular cone of height h. So we are going to do that and we're going to solve it using the method of integration. So first you can see I've drawn out a little hemisphere and we're going to use integration to find the center of mass of this hemisphere. So to do that, the first thing I'm going to do is to define a density. I'm going to say let the density, let's say sigma, be the density, and here since we have only a shell and there's no internal material, I'm going to say the density as the mass per unit area. So I'm going to say instead of density, the mass per unit area. So basically it's another form of density, but this density is area density. We are checking the surface area, and based on the surface area we can multiply that by sigma to get the mass of that object. So given this, we have a hemisphere here. The total area is going to be half of the total sphere's area, which is going to be 2 pi r squared or 2 pi a squared. So 2 pi a squared sigma is the total mass. So now what I'm going to do here is to consider integrating this hemispherical shell somehow, and while integrating we're going to have to multiply the mass of a certain integrated component with its position on the x-axis or y-axis of its center of mass, and I'm going to divide that by the integral of the total masses in order to find the center of mass. So basically the general format here is to have the integral of delta m x divided by the integral of delta m, and this is going to give you the x coordinate of your center of mass. Now you need to do the same thing for your y coordinate, and then you can find the x coordinate and y coordinate of your center of mass. So for this, what we're going to do first is to say and let's say we use g for the symbol here, g given by x bar comma y bar be the center of mass. So we can say be the center of mass. So here what we're basically going to do is to try to find the coordinates of x bar and y bar of the point G, which is the center of mass of this object. Now here we have x bar and y bar, but you'll note since this object is radially symmetrical about the x-axis, meaning that no matter where you take on the x-axis, around it it's entirely symmetrical, there is not going to be any y bar coordinate. It's going to be equal to 0 because the center of gravity here of this entire object must be on the x-axis, and therefore y bar must be equal to 0. So we can say by radial symmetry, in this particular situation, by radial symmetry, since the entire object is radially symmetrical, the y bar or the y coordinate of the center of mass must be equal to 0. We can say by radial symmetry, y bar equals 0. So now all we need to do is to find x bar, which is the x coordinate of the center of gravity or center of mass of the entire object. So to do that, we need to use integration, and as it turns out, it's easier to use integration in polar coordinates than integration in linear coordinates for this particular object. So what I'm going to do is to integrate by polar coordinates, and in order to do that, what I'm going to do is to draw a line like this from the center of the hemisphere until we get to the surface of the hemisphere, and I'm going to say the angle here is equal to theta. So since this is a radius, the hypotenuse here is equal to a, and the angle here is equal to theta. And then I'm going to suppose that I draw another line like this, such that the angle difference between these two is a little angle d theta, which is the angle that we're going to integrate with respect to. So considering this, what I'm going to do is to create a little object that we can use to integrate this entire object. The little object I'm going to create is a little ring, which is going to be part of the entire object that we have here. It's going to be a little ring-like segment of the entire hemispherical object that we have. So that ring is going to go around the hemisphere like this, from the point of contact at this point right here, and the point of contact at this point right here. And then these 2 points are going to isolate a little ring that is going to go around it on the other side like this, but we can't of course see that. And this little object here is going to be the ring that we're going to be integrating from theta equals 0 up to theta equals 90 degrees. So considering this ring, if you take a look, you can see the ring is like this. The ring's geometry is like this. We have a ring, it goes around like this, and in terms of the ring's values, we can see if the height here is going to be, or the hypotenuse here is going to be a, then the height here, which is going to be the radius of the ring, is going to be a sine theta. So therefore the radius here, this height, is a sine theta. Now if the angle change here d theta is very small, then the vertical height of this point and this point are also going to be approximately equal. So if you take the limit as d theta approaches 0, we're going to get that these two heights are basically equal. So if the two heights are basically equal, then this little ring-like object actually turns into a cylinder. And considering that cylinder, the curved surface's length here is going to be a, the radius, times d theta. So this curved surface is going to be a d theta, and in the limit that means that this flat surface here in the limited cylinder is also going to be equal to a d theta. So this length is a d theta, and the height here, the radius, is a sine theta. So we have a little cylinder basically of radius a sine theta and a height here of a d theta. Now considering this little cylinder, the surface area of the curved surface here is going to be equal to 2 pi times the radius times a d theta, 2 pi rh. So therefore, the curved surface area here of the little ring that we're going to create is going to be 2 pi times radius, which is a sine theta, so 2 pi a sine theta times a d theta. This is going to be the little surface area of the external curved surface of the little ring that we're going to have. Now considering this, if sigma is the mass per unit area of the entire object, then the mass of the little ring that we're integrating here is going to be sigma times 2 pi a sine theta times a d theta. So therefore this right here is going to be the mass of the little ring. Now considering the center of mass of the little ring, we can see since the little ring is also radially symmetrical, the y coordinate of the center of mass is going to be 0, but considering the x coordinate of the center of mass, we can see it is going to be from the origin here a distance of this much from the origin, and we can see based on this triangle, if the hypotenuse here is a, then the distance here is a cosine theta. So therefore the x coordinate of the center of mass of this little ring here is a cosine theta. Now in our integral, we need to integrate delta m times x divided by the integral of delta m. So the x here is a cosine theta, meaning that what we need to integrate is delta m, which is this thing, multiplied by a cosine theta on top, and on bottom we need to have the integral of this expression right here. So now if I do that, if I set up the integral, we can say that the x coordinate of the entire object that we're going to create here, which is the hemisphere, which I'm going to say as x bar, since we defined it as x bar up here, x bar is going to be equal to the integral of delta m times x down here, delta m times x, which delta m is this and x is this. So therefore the integral of sigma times 2 pi a sine theta times, and we have a d theta, but then we multiply by x, which is a cosine theta, and I'm going to take the d theta to end and say this is going to be equal to a, this part, times the x coordinate, which is a cosine theta integrated with respect to theta, and this needs to be divided by the integral of just the mass delta m, which in this case is this expression right here. So we have sigma times 2 pi a sine theta times a integrated with respect to theta. Now considering the limits of this integral, we can see if we look at the diagram up here, if I erase the short work, looking at the diagram up here, the smallest ring that we can create is this ring right here at the very end, and that ring gets created when the angle theta is about 0. And the largest ring we can create is this ring right here, and that ring gets created when the angle theta is 90. So therefore the limits here are the limits from 0 to 90 degrees or pi by 2 radians, and here as well the limit is from 0 to pi by 2. So therefore this expression right here is going to give us the x coordinate of the center of mass of our object. Now again, as I said, the y coordinate is not necessary since it's equal to 0 by symmetry, so all we need to do in this situation is to find the x coordinate. So if I simplify these two integrals here, I can say that x bar is equal to, and in these two integrals we can see there are a lot of constants that I can take out. Sigma is a constant, 2 pi is a constant, a is a constant, here a is a constant, and here also a is a constant. So if I take all of them out, we can see on the top integral we have 2 pi times sigma times, here we have one a, another a, and another a, so we have a cubed times the integral from 0 to pi by 2, and what we have left over is a sine theta here, a cosine theta here, d theta. So we have sine theta, cosine theta, d theta. On the bottom, if we consider that integral, the integral here has some constants of sigma, 2 pi, 1a, and another a. So we have 2a. So we have sigma and 2 pi and 2a. So we have 2 pi sigma a squared times the integral from 0 to pi by 2, and considering the inside we have sine of theta d theta. So we have sine theta d theta. Now considering the constant on the front, we can see they all cancel, all of these cancel except for a here, so we can get that x bar is equal to a times the integral on top divided by the integral on bottom. Now considering the integral on top, we can see we have sine theta times cosine theta d theta. If we consider letting u equal sine theta, we can see taking the derivative, du is equal to cosine theta d theta. Therefore, if we substitute u equals sine theta, we can see the cos theta d theta becomes du, and therefore the integral here is the integral from 0 to the corresponding value of u, which in this case, if sine theta is equal to theta is equal to pi by 2, sine theta is equal to 1, so therefore 0 to 1 of sine theta is u, so we have u, cos theta d theta is du, so we have du, so this is going to be equal to the integral of u is going to be u squared over 2 from 0 to 1. So if we substitute this, we can see we are going to have the integral of sine square theta divided by 2 from 0 to pi by 2, which is basically the same exact thing as integrating u squared divided by 2 from 0 to 1. Now considering the bottom integral is easy. We know that directly the integral of sine theta is going to be cosine theta. So therefore, if we divide that, we are going to divide by cosine theta going from 0 to pi by 2. My apologies, I made a small mistake here. The integral of sine theta is not cosine theta, it's negative cosine theta. So we have negative cosine theta. So now, considering the integral here, we have x bar equals a times, and the integral on top is sine squared of pi by 2 divided by 2 minus sine squared of 0 divided by 2. The integral on the bottom is going to be equal to negative cosine of pi by 2 minus negative cosine of 0. Now evaluating the top integral, we can see x bar is equal to a times, this is going to be 1 divided by 2 minus 0 divided by 2. So we can see we have 1 over 2 or half minus 0. So the integral on top is going to be equal to half. So we have a half on top, and on bottom we can see cosine of pi by 2 is equal to 0. So we have 0 here, and on bottom this part here is going to be minus 1. So we have minus 1, which is going to be 1. So we have 0 plus 1, which is going to be 1. So therefore the integral on bottom is 1, meaning that we finally get that x bar is equal to a times a half, or a over 2. So with this we can see that the distance from the origin or the center of this hemispherical shell here to the point at which we have the center of mass is a over 2, as was described in the question. So we have solved the first part of the question and found the distance a over 2. Now the second part of that same question, we have to find the center of mass of a solid, uniform, right circular cone of height h, which is at a distance of a over h over 4 from the center of the base. So considering that, if we go down, we're once again going to use integration. Here you can see I've drawn the height h here. I also assumed a radius of r here, and we're going to start this question by saying the density is a certain value. But here, since we have a solid cone, the volume is actually what's important. So therefore I'm going to say let sigma be not the mass per unit area, but this time the mass per unit volume. So now we have that. So let sigma be the mass per unit volume. Now given this, we're going to again define like we did above the center of mass and say that let G be given by, let's say, x bar comma y bar be the center of mass. Now considering the geometry here, we can see since this cone, similar to the above object that we had, is also radially symmetrical, it is similarly radially symmetrical about the x-axis, we can say that the y-coordinate of the center of mass of this cone must be equal to 0, since it is radially symmetrical. The coordinate of that point here, G, must be somewhere on the x-axis, meaning that y bar is equal to 0. So we can say once again, by radial symmetry, again y bar is equal to 0. Now this is often the case in a lot of integrals, but sometimes in these kinds of questions they might give you objects where y bar is not equal to 0, i.e. the object is not radially symmetrical. If they give you that, then you will have to find using integration both x bar and y bar. But in this case, since we don't have to do that, since it's radially symmetrical, we only need to find x bar. Now for x bar, as we did previously, x bar is going to be equal to the integral of delta m x divided by the integral of delta m. Now all we need to do is to find the value of delta m and the value of x. So considering the object that we have here, the easiest way to integrate this object would be to integrate it linearly. So what I'm going to do is I'm going to integrate it linearly by considering a small portion like this of the entire cone. I'm considering a small portion like this, and let's suppose that this is the origin, and let's suppose that the distance from here to here is what I call the variable x. And let's suppose that the small distance from this point to this point in the x-coordinate direction that I go is dx. So now we basically established different coordinates that we're going to integrate with respect to. So now what we need to do is to find the volume of this shape, which we can then use to find the mass of the shape, and then we need to find the distance of the x-coordinate of the center of mass of this object from the origin. Now, considering the first part, this object is approximately a cylinder, and as dx gets really small, then the height difference here gets really small, and we get an approximate cylinder which is going to be having these dimensions. It's going to be a cylinder like this with a circular base on this side and a circular base on this side. It's going to have a height here of dx, and it's going to have a radius here of, according to this, if the distance here is x and if the angle here is alpha, we can see we're going to have here tan alpha is equal to the radius divided by x, meaning that the radius here is x tan alpha. So we have the radius here being equal to x tan alpha. Now, considering the value of tan alpha, we can see if the radius here is r and the height here is h, we can see this is going to be h, this is going to be r. In the same triangle, we can see if we take tan alpha in this large triangle, then we have r divided by h, and therefore tan alpha is equal to r over h. And therefore, considering this cylinder, we have x times r over h, and therefore we have x r over h as being the radius of this cylinder. So we have this radius and we have this height, meaning that the volume of the cylinder is pi r squared h, which is going to be pi xr divided by h squared times h, which is in this case dx. So the height is dx, meaning that this is the volume of one of these small cylindrical segments. Now, if this is the volume and we have the sigma being equal to the mass per unit volume, then the mass of one of these little cylinders is sigma times all of this. So therefore, delta m here is equal to sigma times pi xr of h whole thing squared dx. So now, considering that, all we need to find now is the x-coordinate of the center of mass of the little cylinder. Now, considering the little cylinder, we can see if the little cylinder is very thin as in dx is very small, then the center of mass of the cylinder is going to be at a distance of exactly x from the origin. So therefore, the coordinate of the x-coordinate of the center of mass of the cylinder is exactly equal to x. So given this, we can now write down the integral, which is going to give us our x bar here. We can write down, removing all of this stuff here. We can erase this thing. We can actually, we'll leave it for now because we need it to substitute in the integral, but then we'll erase it. We can erase this thing, make this thing up here, and then we can say the integral is going to be, the integral we're going to have are going to be x bar equals integral of delta m times x, which in this case is going to be sigma pi xr over h squared times x dx divided by, and the second integral down here is just going to be integral of the mass, so it's going to be the integral of sigma pi xr over h whole thing squared dx. Now, considering the limits of integration here, we can see the x-coordinate starts from x equals 0 and it ends at the maximum value of x equals h. So therefore, we need to integrate here from 0 up to h. Here also 0 up to h. So considering these two integrals, we can see there are a lot of constants inside the both of these integrals which you can take out. So taking them out, we can see the top integral has sigma pi, and here if we expand this thing, we're also going to get an r squared divided by h squared. So if we take them out, we have sigma pi r squared divided by h squared times the integral from 0 to h of, on the inside, we're going to have x squared times x dx, which is going to be equal to x cubed dx. Now for the bottom integral, we can see we also have sigma pi, we also have r squared divided by h squared as the constant, so we have sigma pi r squared divided by h squared for that one as well. And considering what's left over, we have x squared integrated with respect to x, so we have integral from 0 to h of x squared dx. Now we can see in this particular case, all of the constants perfectly cancel. All of this cancels for all of this, leaving us with x bar equal to the integral from 0 to h of x cubed dx divided by the integral from 0 to h of x squared dx. Simplifying this down, we can see we're going to get x to the power of 4 divided by 4 from x equals 0 up to h divided by, and here the integral of x squared is going to be x cubed divided by 3 from again 0 up to h. Substituting in, we can see we have h to the power of 4 divided by 4 minus h to the power 0 to the power of 4 divided by 4 divided by h to the power of 3 divided by 3 minus h to the power of 3 divided by 3, which is simplify 0 to the power of 3 divided by 3. Simplifying down, we can see we have h to the power of 4 divided by 4 divided by h to the power of 3 divided by 3, which is going to simplify to 3h over 4. So the distance here is 3h over 4. Now this distance is the distance from the origin to the center of mass. So this tip here, the tip of the cone to the center of mass, which is somewhere over here, is 3h over 4. But if you recall in the question, that is not what we wanted. What we wanted is the distance from the base of the cone, the center of the base of the cone, up to the center of mass, and that's going to be h over 4. So we can see here, since 3h over 4 is the distance from the tip of the cone until the center of mass, the distance from the base of the cone until the center of mass must be equal to h minus the value that we just got. So we can say that therefore, the distance from the center of the base of the cone to the center of mass is equal to the total height h minus the distance of the center of mass from the tip of the cone until, which is the origin, until the center of mass, which is going to be equal to 3h over 4. And we can see that's going to give us h over 4, which is the answer that we want. So we can see the final answer we get is in fact h over 4. We can underline that, and now we've completed the very first part of the question. Now for the next part of the question, we need to show that if the part of the cone here that we're cutting out has a mass of m, then the rest of the frustum that we have has a total mass of 26m. Now to do this, what we're going to do is to go down, just draw the diagram really quick so that we can get an idea of the system that we're dealing with here. We have a cone here, and we're cutting the top off, and in this cone's upper cone's radius is a, the height is a, and the total height is 3a. So therefore, if this height is a, then this height here is 2a, so a and 2a, and the base radius of the large cone is 3a. So now here, if the volume of this thing is equal to, let's say, V upper or something for upper cone, then V upper here, V upper is equal to, according to the formula for the cone's volume, 1/3 pi r squared h. Now in this case, r is equal to a, so we have r squared, and h is also equal to a, so we have times a. So we have 1/3 pi a cubed. Now considering that if the mass here, if the mass is m, then density, which I'm going to say calls, let's say, density rho, is equal to mass over volume, which is going to be m divided by 1/3 pi a cubed. And then let's suppose that the rest of the cone here has a volume called how do you say, let's say V frustum, because the frustum is the object we're looking for here. So V frustum plus the V upper, which is the upper cone's volume, is equal to the total volume of the entire cone here, which is having a base radius of 3a and a height of 3a. So therefore we have 1/3 pi r squared, so 3a squared h, which is also 3a, and we can see we're going to get 27 times 1/3 pi a cubed. So we have exactly 27 times the total volume that we had earlier, and therefore we can see that V frustum is equal to this thing minus V upper, which is going to be 27 times 1/3 pi a cubed minus V upper, which is going to be equal to 26 times 1/3 pi a cubed, since V upper is also equal to 1/3 pi a cubed. And therefore, if we can finally write down that the mass of the frustum is equal to the volume of the frustum, V frustum, times the density rho, which is going to be equal to 26 times 1/3 pi a cube times the density, which is m over 1/3 pi a cube. Cancelling out the 1/3 pi a cubes, we are left with 26m. So we can see the answer is 26m. Now this is kind of obvious, like we don't really need to do all of this, but because they've asked us to do it, we'll do it like that. You don't really need it. I mean, you can clearly see this cone, the large cone, is going to have 27 times the volume of the smaller cone. So therefore it's going to have 27 times the mass. And if the mass of m here is removed, the total mass is 27m, then obviously the remainder is going to have a mass of 26m. But for whatever reason they've asked us to solve it like this, so we'll solve it. So now we've obtained 26m. And we can move on to the next part of the question. So the next part of the question says, we fix a hemispherical shell of radius a and mass m onto the rod of length lambda a and mass m with the frustum on the bottom like this to create a composite object like this. Now in this composite object, they are saying that the distance of the center of mass from the center of the large circular base of the frustum, which is this point right here, is 3 over 56 rather, times 15 plus lambda times a, where lambda is the constant that we have here. So how do we solve this? Well, to solve this, we need to consider the distances of each of these individual object components, centers of mass, from this point right here, and of the masses, and then we're going to take the product of each of the individual objects' masses and their distances of the center of gravity from this point, and divide that by the total mass in order to finally get the distance of the composite center of gravity from the origin, which is going to be right here. Now when solving this kind of question where you need to find the center of mass of a composite object, the usual pattern is to draw a table. This particular table right here. So you can see this table contains 3 columns. The first column is the object column. In this column, you will generally draw a diagram of the object that you're considering, be it either a simple object or the final composite object that we're considering, and then you will mark out some dimensions and use that to fill in the other 2 columns. The second column is the mass column. In this column, you will write the mass of the object that you're considering. And the final column is the distance of the center of mass column. In this column, you will write the distance of the center of mass of the object you're considering relative to some common reference point. In this case, for this question, the reference point is the point O, which is at the base of the large cone here, like so this point right here, and we're measuring the center of mass of all the objects above that point. So, what you will do in this kind of table is to have your composite object at the very end, and then you're going to break your composite object into simple objects that you can find the center of masses of easily, either by integration as we did above, or because they're so obvious that you can very easily find them. So if you can break your object into simple objects like that, for example, here I have the hemisphere, I have the rod, which is a simple object. I can easily find the center of mass at the middle of it, and I also have the frustum, which is actually broken into 2 pieces. The frustum is broken as the large original cone and the small cone that we cut off from the tip. So here, the mass of the small cone is going to be negative and the mass of the large cone here is going to be positive, because we're removing the small cone from the top of the large cone. So you will see how that works. So now what we're going to do is to fill in all of these columns. We're going to fill in all of the mass columns, and then we're going to fill in all of the distance of the center of mass columns, and finally we're going to take the product of this thing, add to that the product of this mass and this distance, add to that the product of this mass and this distance, and finally add to that the product of this mass and this distance, and say that that total product sum is going to be equal to the product of the mass of the total composite object times the distance of the center of gravity of the composite object from the origin O. So, going up, if we start filling, the total cone which we found earlier had a mass of 27m. The small cone that we took from the top had a mass of m, but the m here is actually negative, so I'm going to put in brackets a negative sign to indicate that the mass m here is being removed from the composite object. After that, we have this little rod of length lambda a here, and that rod has a mass of m, so I'm going to say m here as given in the question. And finally, the hemisphere also had a mass of m. So considering the total mass here, we have 27m, we have a negative m, we have a plus m and a plus m. Adding them together, we have 27m plus m minus m, which is going to give us 28m in total. So therefore, the total composite object here must have a mass of 28m. 26m coming from the frustum, one m coming from the stick here, and one final m coming from the cup, little hemisphere thing, the cup at the top. So now we have all of the masses written down. Now we need to consider the distances of the center of mass from the point O above the point O. Now at first, we have a cone. The cone has a height of 3a. As we found, the distance of the center of gravity above the base of a cone is going to be 1/4 of the height. We found above here, if the total height of the cone is going to be h, then the distance from the base is going to be h over 4. So therefore here, if the height is 3a, then the distance above the base, which is what we want, of the center of mass is going to be 3a over 4. Now for the next cone, this cone's base starts at a height of 2a over here. The height here is already 2a. And in addition to 2a, the cone's height is a. So therefore, above its base, it has a height of a over 4 for its center of mass. But that a over 4 is already above a height of 2a above the base O. So therefore, the total height above O that this cone here has its center of mass is going to be the distance 2a plus the bonus distance from its base up to the center of mass, which is a over 4. So 2a plus a over 4. So I'm going to write here 2a plus a over 4, which I'm going to simplify with a taking common denominator of 9a over 4. Now moving on for this little rod here, the rod is starting at a distance of 2a above here, so it's at a distance of 2a, but then the center of mass of the rod is going to be at the middle of the rod since it's a uniform rod, and therefore the height here is lambda a divided by 2. So therefore the total height above the point O is 2a plus lambda a over 2. So writing that down, we can say the total height of the rod center of mass above is going to be equal to 2a plus lambda a divided by 2, which if you take a common denominator is going to be equal to 4 plus lambda over 2a. Now moving on, the next thing is the hemisphere. The hemisphere is at a total distance of 2a plus lambda a above O, but then the center of mass of the hemisphere is a over 2 from the top like this. So therefore, since the total height here is also a, since that's the radius, it is going to be a over 2 from the point that the stick connects to the hemisphere above that point. So therefore, this distance here is going to be a over 2. So we have a over 2, we have lambda a, and another 2a. And therefore, the total distance above the point O that the center of mass of this hemisphere is going to be equal to 2a plus lambda a plus a over 2, which if you take under a common denominator is going to be equal to 2a becomes 4a plus a becomes 5a plus lambda 2 lambda a, so it's going to be 5 plus 2 lambda divided by 2a. Now finally, considering the mass here and the center of mass, we're going to call this x bar, which we can then use as 28 times x bar in our final answer, and then we can rearrange that to eventually get x bar equals something. So now with this we can finally find x bar by saying that the products of this mass times this distance plus this mass times this distance plus the next mass times the next distance and so on up to this mass times this distance is going to be equal to the total mass times the total distance. So therefore if I go down here and write down, I can say 27m times 3a over 4, 27m times 3a over 4 plus the next thing, which the next mass is minus, so I'm actually going to write minus m times 9a over 4, so minus m times 9a over 4. The next mass is plus, it is m, and 4 plus lambda divided by 2a, so we have m times 4 plus lambda divided by 2a plus the final mass is m times 5 plus 2 lambda divided by 2a. So m times 5 plus 2 lambda divided by 2a, and that has to be equal to the total mass of 28m times the total distance of x bar. And now we can solve for x bar. So considering this thing, everything has an m in it, so we can cancel all the m's out, and then we can take the 28 to the other side and write that x bar is equal to, actually, we'll leave it for now. We'll leave it as 28 x bar, and we'll simplify everything, and then we'll take the 28 to the other side. So here, considering what we have 27 times 3 over 4, so we have a total of 81 a over 4. Then we have minus 9a over 4. We'll try to take everything under common denominator of 4. So doing so, we have, if we take a 4 on top and bottom, we are going to have a 2. So we have 8 plus 2 lambda a. So we have 8 plus 2 lambda divided by 4 a plus, and then this thing taking common denominator of 4 rather, is going to become 10 plus 4 lambda. So we have 10 plus 4 lambda divided by 4a. Now, taking everything together, we have 28 x bar equals 81 minus 9 plus 8 plus 10. So we have 81 minus 9, which is going to be, actually we can make it easy. 10 plus 8 is 18. 18 minus 9 is plus 9. So therefore we have 81 plus 9, which is going to be 90. So we have 90. And then we have 2 lambda and 4 lambda, 6 lambda. So we have total of plus 6 lambda divided by 4 times a, which we can see here. We can factor out some stuff, and if we do that, we can see we can divide by 2 here to get 45 plus 3 lambda. So we get x bar equals 1 divided by 28 times 1 divided by 2 is going to be divided by 56. On top we have 15 times 3 plus 1 times 3 lambda. So we can take a 3 out. Then we have 15 plus lambda a, and that is the answer that we wanted. So therefore we've solved that part of the question. We found the answer. The answer is 3 over 56 times 15 plus lambda times a. So we've solved the final answer for that part of the question. So finally, for the last part of the question, we are told that we put this thing on the edge of a table, and when we do that, it does not topple. So it's in equilibrium. So if it is in equilibrium, we are asked to show that lambda must be some value less than or equal to 11 over 3. So that must mean that if lambda is greater than 11 over 3, then this stick would be too long, causing the whole thing to topple due to the center of mass being too far forward. So what we're going to do is to analyze the situation here, and then we're going to consider the geometrical facts we can derive and use those facts to show that lambda must be less than or equal to 11 over 3 for this thing to be stable. So the first fact we're going to draw is the fact that the angle at the base here is 45 degrees. We can see the angle at the base here is 45 degrees because, as we know, the total height of this thing is 3a and the base radius is also 3a. And due to that, if you consider the tangent of the angle here, tangent of, let's say, alpha must be equal to 3a divided by 3a, which is 1, and therefore the angle here must be pi by 4. So we can say that we have 45 degree angle here. Now, since these two sides are parallel, we also know that if we put a vertical here, this angle is also pi by 4. So now I'm going to use that fact, and I'm going to draw a little dotted line through the central axis of symmetry of this object, like so. If I just draw this dotted line like this, you can see the center of mass of the object must be somewhere along this dotted line, where the point right here is the point O. But now, since this point right here is the final point where we have a contact between our object and the table, we must have that the center of mass is somewhere to the right side of this vertical line here. Because if it's not, if it's to the left side of the line, then we can see, dropping the center of mass down to the table, it is outside the supporting base of the object. And as we know, if ever the center of mass is outside of the supporting base of an object, the object is going to topple because the total moment will be outside, causing a toppling effect. So we can say that if the center of mass here is anywhere to the left side of this line right here, the vertical line that I've drawn, then it's going to topple. So therefore, if it's not toppling, it must be to the right side of the line. Now, considering that, we have to find exactly where this line cuts the axis going through the central symmetrical axis of this object. Because if we can do that, then we can find the distance from O to this point. Now I'm going to suppose that this point right here is called, let's say, A. And let's suppose that this point here is called B, this point here is, let's say, C, there's a 90-degree angle here, and let's suppose that the point G, which is the center of mass, is somewhere over here. So we know that OG is equal to 3 over 56 times 15 plus lambda times A. We know this. Now, we need to find the point A. So considering the point A here, due to geometry, if this angle is 90 degrees and these two lines are parallel to each other, then the angle here must also be equal to 45 degrees. Now, considering the geometry, because the total height here is equal to 2a, since the frustum, as we know, is equal to 2a, the height here is equal to 2a, and the base radius here is equal to 3a, we know that this distance here, CB, is equal to a. Since if this was continuing like this to make a complete cone, then the total cone radius here would be a. So therefore we know that CB is equal to a, and therefore we can say, since the angle CBA is equal to 45 degrees, the tangent of the angle is going to be equal to 1, and therefore CA is also equal to a total distance of A. Now if CA is equal to A, then since OC is equal to OA plus AC, we can say that OA distance, which is what we want, which is the maximum distance that we can have for the OG length, is equal to 2A, which is OC, minus AC. So we can say is equal to 2A minus A is equal to A. And therefore OA length is equal to A. Now we can say, if the system is in equilibrium, if the, we'll say, object is in equilibrium, we can say that the OG length must be less than the OA length. So now given this, we can substitute the OG length in and the OA length in. The OG length is this thing right here, so we can say 3 over 56 times 15 plus lambda A, 3 over 56, therefore 3 over 56 plus times 15 plus lambda A must be less than OA, which is less than A, and therefore the whole thing must be less than 1. So we can say, rearranging, 15 plus lambda must be less than, if we take this to the other side, we get 56 divided by 3. Therefore lambda must be less than 56 divided by 3 minus 15, which if you take under common denominator of 3, we're going to have lambda must be less than 56 minus 45 divided by 3, and therefore finally you can see lambda must be less than 11 over 3. And hence we have solved this question. This is the final answer in this question. So now let's finally discuss the marks awarded for this question. So at the start of the question, for integrating, when you consider the first thing and you say let G given by x bar comma y bar be the center of mass, and you define it and say biradial symmetry y bar must be equal to 0, for this itself you get 5 marks. Now after that, when you construct the integrals based on the diagram here and you write the top integral, you get 5 marks, and also for the bottom integral you get another 5 marks. When you then solve these two integrals and then you apply the limits like this and this, for the top integrals limits you get 5 marks, and for the bottom integrals limits you get another 5 marks. And finally, when you get the final answer of a over 2, you get another 5 marks. Now for the next part, when you solve the solid cone, again for defining center of gravity like this and saying that biradial symmetry y bar must be equal to 0, you get another 5 marks. After that, when you integrate, setting up the two correct integrals like this and this gets you 5 marks and 5 marks for the top integral and bottom integral, but then solving the two integrals with the limits gets you only 5 marks, and getting the correct integral answer gets you another 5 marks. Now I think probably the reason they only give you 5 marks and not 5 marks for the top and 5 marks for the bottom is because these integrals are relatively easy. They only have x to the power of n integrals. So therefore the whole thing gets you 5 marks, and the final answer here gets you 5 marks. And then after that, when you say that this final answer obtained is the answer for the distance from the tip of the cone until the center of mass, and therefore the distance from the base until the center of mass is going to be h minus that value, which is h over 4, you get another 5 marks. Now after that, for showing that the frustum has a mass of 26 m, when you write down some kind of density like this, you get 5 marks. And then when you subtract and get the correct volume of the frustum by subtracting the total cone from the little cone that we remove, you get 5 marks. And finally, when you write down the correct answer of 26 m, you get another 5 marks. Now after that, in this table, when you write down the mass of the large cone as 27 m, you get 5 marks. And then when you write down the distance, you get another 5 marks. And for over here, writing these masses doesn't get you any marks, probably because these masses were given directly to you in the question itself. These masses were given, so because of that, you don't get any marks for the masses. However, you get marks for this distance, 5 marks, this distance, 5 marks, and for the distance of the center of mass of the hemisphere, you get total of 10 marks, probably because the expression for it is a little bit more complicated. We have 2a plus lambda a plus a over 2. And then finally, for writing down the total mass of the object as 28 m, you get 5 marks, and writing down its center of mass having a distance of x bar, you get another 5 marks. Now you could also write it like this, or define it with a sentence or something, that will also get you the same 5 marks. Now after that, when you then say that these two objects are equivalent and therefore the sum of all of the masses times distances must be equal to the total mass times total distance, we are going to get a total of 5 marks for writing the entire equation correctly. It also should be noted that if you make any mistakes here, you don't get any of the marks. Any of these 10 marks, all of it will get cut by making a single mistake. Now after this, when you simplify and eventually get x bar equals 3 over 56 times 15 plus lambda times a with the correct steps, you get 10 marks for that. For the final part of the question, when you then consider the equilibrium of this object and you find the distance CA here and then the distance OA here, for the finding the distance OA as A, you get 5 marks. And then I have actually made a mistake here when I was explaining. I wrote less than but not less than or equal. The actual correct case is less than or equal due to the fact that at the exact point when OG equals OA, i.e. G equals A, it is also stable. So this should not be a less than sign, this should be this sign, the less than or equal sign. So when you say if the object is in equilibrium, then OG is less than or equal to OA, you get 5 marks. And after that, when you then substitute the value of OG and OA and simplify down to eventually get that lambda is again less than or equal to 11 over 3, you get another 5 marks. And that is the end of the question. So I hope you enjoyed. If you have any feedback, post them in comments down below. Thank you for watching and goodbye.